Good morning. It's April 9th, and this is your daily brief in science. Here's everything you need to know. ModeX Therapeutics has begun a Phase 1 trial of ModeX 2301, a tetravalent bispecific antibody designed to neutralize all known SARS CoV-2 variants, with initial dosing in healthy and high-risk adults. The study's primary endpoints focus on safety and tolerability, while secondary objectives look at pharmacokinetics, anti-drug antibodies, and neutralizing activity. This randomized, double-blind, placebo-controlled dose escalation trial will evaluate safety and tolerability across intravenous, intramuscular, and subcutaneous administration in up to 80 participants. The trial is funded entirely by U.S. federal funds from HHS BARDA under Contract 75A50123C00056, described as non-dilutive and not an endorsement of results. If successful, ModeX's multi-specific platform could have broader applicability to other infectious threats beyond COVID-19. ModeX Chief Scientific Officer John Mascola calls this milestone pivotal for the multi-specific antibody platform, highlighting potential for expanded breadth and durable protection. Executives from ModeX and OPKO stress the trial's public health importance and the prospect of broader protective strategies beyond traditional monoclonal antibodies. ModeX Therapeutics, based in Weston, Massachusetts, focuses on multi-specific biologics for cancer, immunology, and infectious diseases, and operates as part of OPKO Health. Gary Nabel, ModeX president and CEO, notes the multi-specific approach could address ongoing SARS CoV-2 evolution with broader, more durable protection. The study is identified as NCT07445971, aiming to enroll 80 participants in this Phase 1 design. A landmark map of the maternal-fetal interface brings unprecedented detail to how pregnancy biology works. Researchers analyzed about 200,000 cells directly and nearly 1 million in their tissue context to identify cell types and states linked to complications like preeclampsia, preterm birth, and miscarriage. By pairing this single cell and spatial data with large genetic studies, they pinpointed which placental and uterine cells carry high-risk genes and are most vulnerable in these conditions. Using genetic data from more than 10,000 patients, they mapped genetic risk signals onto DNA regulatory regions to identify the exact cell types and states involved. The study, published in Nature in 2026 with Lee and colleagues as primary authors, was released and widely disseminated on April 8, 2026. The placenta serves as a temporary organ connecting fetus to mother and drawing on maternal blood to support growth. The findings may help explain associations between cannabis use during pregnancy and risks such as reduced placental blood flow and fetal oxygen delivery, though cannabinoids are not the sole cause of these outcomes. Foundational obstetric literature is cited to place the work in context of placental biology. Project leaders say the level of detail achieved is unprecedented and could deepen understanding of normal development and pathology at the maternal-fetal interface. The Nature article summarizes Wang, C. et al.'s single-cell spatio-temporal dissection of the human maternal-fetal interface. Beyond basic science, the work demonstrates the promise of single-cell multi-omics and spatial data for precision medicine in reproductive biology and informs public health discussions about cannabis use in pregnancy. A newly identified maternal cell type at the entry point of fetal placental cells bears cannabinoid receptors and acts as a regulator, potentially limiting placental invasion when exposed to cannabinoids. This novel cell type appears to function as a speed bump at the maternal-fetal interface, modulating invasion depth to prevent over- or under-invasion by fetal cells. Nighttime lighting is changing across the globe for many reasons, from urban growth to disasters and shifts to LED tech, and it can reflect a country's development and stability. A new analysis uses more than 1 million daily satellite images to map these changes day by day, offering a granular view beyond older yearly data. The study finds that overall light emissions rose in some regions, while others declined, with Asia showing gains and Europe moving downward. In the United States, nighttime light increased about 6% overall, driven by West Coast tech activity and population growth, while the East Coast and Midwest dimmed as areas de-densified and energy-saving lighting spread. Brightening occurred mostly in emerging economies, notably in sub-Saharan Africa and Southeast Asia, led by Somalia, Burundi, Cambodia, and others, while the United States, China, India, Canada, and Brazil recorded the highest totals in 2022. Europe is trending toward lower night lighting due to energy-efficient LEDs, anti-light pollution policies, and broader efficiency measures, with France highlighted for notable late-night reductions under regulatory and dark sky initiatives. The authors argue that nocturnal light intensity can serve as a proxy for socioeconomic development because lighting changes mirror technological progress, political shifts, and economic stability. Overall patterns show urbanization, infrastructure expansion, and rural electrification driving brightening as indicators of greater energy access, while dimming often signals crises or deliberate conservation efforts. The study emphasizes that reducing light pollution remains important for ecology and astronomy, even as policy and infrastructure shape regional trajectories. In a tiny, confined arena, E. coli bacteria generate rotation on microscopic discs without any physical contact, a phenomenon driven by the swarm's collective motion. Thousands of swimming bacteria spin their bodies and flagella in opposite directions, creating net rotational fluid flows that impart torque on the discs. These discs, dubbed hockey pucks, are set in motion by the active bath fluid dynamics produced by the bacterial swarm. The study shows microscale life can drive complex physical processes and enable motion at micro and nanoscales without direct contact. Funding for the work came from the European Research Council under the Horizon Europe program, VULCAN, Project 1010869998. This research sits within the broader field of active matter, where energy input from moving components leads to emergent, organized motion. Potential applications include microscale manufacturing and soft materials, where bacterial active baths could function as contactless, shape-sensitive rotational engines. The work describes a new type of contactless engine powered by microbial activity, with potential uses in self-organizing soft materials, medical therapies, and sustainable technologies leveraging biology. Bacterial-driven rotation in confined environments appears to be a general phenomenon, with implications for designing micro-engines and medical or sustainability applications in tight spaces. Remarkably, rotation can be triggered by a single bacterium moving through a confined channel, highlighting the system's high sensitivity and efficiency. The effect is mainly governed by fluid dynamics and confinement rather than disc shape, suggesting possible natural occurrences in soil, tissues, or microbial communities. The researchers used perfectly smooth, symmetrical microdiscs created by three-dimensional nanoprinting and found rotation occurs even without asymmetry, challenging the idea that irregular shapes are required. A new study identifies GSK3-alpha as a universal checkpoint that preserves stem cell identity across multiple states and species, redefining how we view stem cell self-renewal. Researchers showed that inhibiting GSK3-alpha supports self-renewal and maintains identity in embryonic stem cells and epiblast stem cells, and this effect extends to neural and formative stem cells. The mechanism is conserved from rats and rabbits to bovines and humans, underscoring its fundamental role in stem cell regulation. The work positions GSK3-alpha as a central molecular node that governs stemness across development stages and species, with implications for culture techniques, aging research, and regenerative therapies. The team, led by Qilong Ying of USC and collaborators from NIEHS, Creighton University, and the University of Michigan Medical School, used advanced methods to dissect signaling pathways and state transitions in stem cells. Key contributors include Duo Wang, USC, and Shukun Wang, NIEHS, with authors from USC, NIEHS, and partner institutions. Funding came from NIH grants, NIEHS intramural programs, and private foundations, with a provisional patent filed on targeting GSK3-alpha for clinical translation. Published in Cell Research on April 9, 2026, the study builds on the ground state concept for embryonic stem cell self-renewal and proposes a framework where a shared checkpoint preserves stem cell state across lineages. The findings suggest broad applications in regenerative medicine, disease modeling, and cancer research by offering a unified view of stem cell regulation across development and species. The research could influence laboratory culture conditions, aging research, and disease modeling strategies, aligning them around a core set of STEMness checkpoints. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.